Okay, let's start. Good morning, everybody, and thank you for coming to today's Black Hole Pyre webinar. My name is Dimitrios Psaltis. I'm at the University of Arizona, and I will be your host for today. Today is the beginning of a series of webinars that we're hosting this spring, somewhat different than our previous webinars, that aim to introduce everybody to the, from the beginning of radio interferometry all the way to using the data analysis and interpretation tools for the Event Horizon Telescope. As I said, this is a series of webinars over the entire spring, and you're more than welcome to register for all of them, and you can find in the chat room the links for the various registrations. The goal of those webinars is to prepare you not only in general to work on your own, but also to participate, if you wish, to the third Pyre Summer School this August in Mexico, in Puebla, Mexico. And again, you can find information in the attached link for that. I also want to point out that not only this webinar, but all the previous webinars are available on YouTube and other channels. And the link is again in the chat. The webinar will be about an hour long, a little less than that. And at the very end, you will have the opportunity to provide feedback through a form that will appear on your screen. Your feedback is very important to us because it helps us improve this in future webinars. So I would ask most of you to please take a minute at the end and complete. It's an extremely short survey for you. Because of the large number of participants, the way that we handle this is that most attendees do not have access to be able to talk. However, we would like to hear from all of you if you have any questions or any comments, either during the talk or at the end, during the Q&A period. So please write your comment or question or a request to talk on the chat on the right of your screen, and then I will give you access to the microphone so that you can give your question in real time. So having said all of that, let me introduce today's speaker, Professor Dan Marrone from the University of Arizona. Dan is an experimental astrophysicist, and he likes to work on really fundamental questions in physics and astronomy, from the very big scales, cosmology and clusters of galaxies, to the very small scales, what happens near black holes, in the black hole in the center of our galaxy. He's aiming to address those questions primarily by building new and modern instruments to make high impact and high resolution observations. And most of those instruments work at sub-millimeter using interferometry techniques. So he's really the best person to explain to us how interferometry works and how we use it to take pictures of black holes. So go ahead, Dan.
Thanks, Dimitrios. So welcome to an interferometry lecture. Under normal circumstances, and including this semester, I would talk for 10, 12, 14 lectures about interferometry. So it's a challenge to think about how to introduce this topic in the course of less than an hour. So what I've tried to do is distill it to a few key points that will enable you to understand jargon and the fundamental measurement that interferometers make, and set up the next lectures that will come, particularly the next one with Lindy Blackburn talking about data properties and data analysis. And there's also, as we go through the talk, I make reference to a couple books, Essential Radio Astronomy and Thompson, Moran, and Swenson, TMS. These books provide a lot more detail. I'll post these slides so you have access to them, but often in the upper right corner, there's a reference to a specific section of one of these books, and you can find a great deal more information there. In particular, TMS is open access, so you can go download it for free as a PDF, or you can buy a copy. All right, so with that said, let's talk about radio interferometers. They look very different depending on the wavelength and depending on what they're trying to measure. Here are several examples. You've got ALMA, which we use in the HT, but you have a co-mounted platform interferometer, now called the YTLA. You have ASCAP, phased array feeds in one of these. And here, even stranger, at very low frequencies, you can have simple dipoles with ground screens arranged in patterns on the ground. And, you know, this just shows you that radio astronomy is covering a wide range of wavelengths and that different detection techniques are required. The interferometry underlying all of these, though, has a lot of similarities, and even the Earth scale interferometry that we do in the Event Horizon Telescope, even though it's not all laid out on the same little patch of ground, fundamentally shares the same measurement idea. So let's talk about what you see when you have an antenna that's composed of, you know, patches of metal. Well, before I do that, let's talk about why you would do this at all. So interferometers are a funny thing because we're going to talk about taking little bits of metal all over the ground, perhaps separated by 10,000 kilometers, perhaps separated by, you know, a few feet, as in this case. And it's not obvious why you wouldn't just use a single telescope. But you know, the key advantages you can gain by using an interferometer are that you can make the telescope you know, bigger, or its surface more accurate locally, or you can point it better or have to not point it as well as you do if you try and make a single telescope of the same collecting area. Basically, all of these properties, the size of the telescope, the accuracy of the surface can hold, and how well it points are connected to each other. Obviously, how well you can point a telescope depends on how big it is. And if you think about it, you have to make very large telescopes to make radio wavelengths have the resolution we're used to at other astronomical wavelengths. So this is just a rule of thumb rule, but the resolution of a radio telescope is 2 arc seconds at a wavelength in centimeters for a telescope diameter in kilometers. And there are not many telescope diameters that are measured in kilometers. So if you want arc second resolution, or micro arc second resolution, as your case may be, you're going to need a very big telescope. And, you know, how are these properties limited? Well, it's a wasted opportunity if you ever give a talk about interferometry and don't show the limits of radio telescopes. So here's the NRAO 300-foot telescope. Here's also the NRAO 300-foot telescope. This was at the limit of what, you know, the size of a single self-supporting telescope. This was a structural failure. There's nothing fundamentally wrong with building a telescope 300 feet across, but it's difficult to do. And so if you want the collecting area of something 300 meters across or 300 feet across or bigger, you know, building it out of smaller separate structures that you can make more accurately and control more precisely is useful, particularly as you go to higher frequency. So if you look at this plot on the right, you see that interferometers are at most wavelengths providing the largest collecting area. So the EVLA had more collecting area than the Green Bank telescope at most wavelengths until the telescope surface reduces the effective area. You can achieve the highest resolution because you can spread your telescopes out by, you know, much larger distances, including the entire Earth. You can also make the resolution elements, the individual elements, smaller so that they capture more of the sky at once, and then resolve that sky into lots and lots of small patches by the interferometric synthesis we're going to talk about. And if you care about knowing exactly where things on the sky, for reasons I won't be able to get to today, you can figure out where they are much more precisely when you're determining position, not by how a piece of metal is steered, but by the arrival time of the light between two telescopes. Okay, so what happens if you compose a telescope out of individual patches of metal? We can understand this problem, at least as a starting point, by asking what happens if we look at, say, a line of metal. We'll do this as a one-dimensional problem. From a distant source. And so just imagine that you have a wire that's transmitting to a distant source. It has an electric field pattern on the wire given by G as a function of the position X. And you can calculate, just by propagating that electric field from each little patch of the wire out to the distant point source, what the electric field pattern will be at that point source from the whole wire. So taking this little black element, the contribution to the electric field at point A is given by the electric field at that position divided by the distance times this exponential factor, which is, you know, the propagation phase of the electric field. And that's simple enough to understand. If you imagine now that A is very far away, you know, in the coefficient, the 1 over r of x becomes just 1 over the distance. But in the exponent, you can't make that go away as easily. And so you can expand it as the distance with some little offset for the extra distance depending on the angle. And so if you rewrite that equation for the differential electric field contribution, you have the electric field divided by distance times a constant phase factor times a non-constant phase factor across the aperture, that second exponential. And then if you integrate over the whole wire, you see, and also, you know, define a new coordinate u that's x over lambda, you see that you have something that looks exactly like, and in fact is, a Fourier transform. The electric field that you would measure at this distant point A is simply the electric field along the wire Fourier transformed to the far field. And so this, you know, fundamental connection between the, you know, pattern on the sky and the pattern on the ground through the Fourier transform is going to be central to the interferometric measurement, and we'll go through it in more detail in a second. All right, I said that. You know, this produces really familiar results. So if you imagine you have a uniform illumination across an aperture, this is what you might have in an optical telescope, say, then the electric field pattern that produces on the sky looks like this sinc function in the middle. And the square of that looks like the very familiar Airy pattern, at least if it's a circular aperture. And this is what we call the point spread function when we're not talking about interferometry. And this is actually, the fact that you can calculate it in this way is really useful, because if you have a telescope surface that's not uniform, maybe it has panels that have gaps, maybe it has blockages, this is a really easy and efficient way to account for the effects of those obstructions in calculating what your telescope will see on the sky. Now, imagine that instead of you having a uniformly illuminated, you know, line here in this one-dimensional case, you have two little patches that are very well separated in space, much more separated than the size of their apertures. They kind of look like delta functions in this plot. What you would see far away is that they respond to the sky in sort of a corrugation, a plane wave across the sky. And so the power response is, you know, strong, straight ahead, where the distance to the two apertures is in equal number of wavelengths, and at zero, where they destructively interfere, where the light is arriving perfectly out of phase. And in fact, if you separate these telescopes by a greater distance, what you get is that your plane wave has a higher spatial frequency on the sky. So the further apart they are, the more rapidly this oscillation in response happens. This is, in fact, simply the Fourier transform of those two delta functions, but you'll have to trust me on it at the moment, or you can calculate it yourself. It's very simple. But let's talk a bit more about what an interferometer actually does. So the place I normally start when teaching this is talking about the simple two-element response. Just imagine that you have two telescopes that are looking in the same direction at some point source, so that we can imagine that there's a plane wave of light coming towards the two telescopes, that source is monochromatic, so we can consider a single wavelength for the moment, or a single frequency. And so the light's coming from the direction up and to the right along those blue lines. And the direction of, or the position of the wavefront is given by that d cos theta horizontal, sort of horizontal line that separates the two telescopes. But of course, because the telescopes aren't exactly the same distance from the source, there's this extra propagation distance, this d sine theta, to antenna 1. And so if you were to put some sort of, receiving element, maybe it's as simple as a wire at the focus of the telescope, and measure the voltage on that wire, what you would see if illuminated by this distant point source is that there's a voltage amplitude times a cosine in time that varies at the emission frequency. And what you're receiving at antenna 1 is delayed by some geometric delay, tau g, compared to antenna 2. And the zoom window is blocking my ability to see what is on my V2, but I trust I wrote it out correctly. And so, all right, simple enough. In interferometry, what we normally do with these two antennas is we correlate them. We take the voltage from each antenna, we feed them into some sort of multiplying thing, and we average that over time. And that gives us out some F, which is the average voltage 1 times voltage 2, as you can see in those equations below. And if you work out the math of that, what you see is that cosine omega t, where omega is 2 pi nu, times cosine omega t minus tau, just breaks into two terms. One that's cosine omega t, and the other one that is varying rapidly, or sorry, omega tau. One that's varying rapidly because it varies with time. It varies at twice the emission frequency. And so when you average over any reasonable time, this term averages to 0 because it's oscillating so quickly. And so this F, this visibility, is simply the voltage amplitude squared times the cosine of some geometric factor. And as the source moves across the sky, as this geometric delay changes, this cosine will oscillate. And so if you take a really simple case where at left I'm plotting time in nanoseconds because I have a 1 gigahertz incident electric field from a 1 gigahertz emitter. And so that time is in nanoseconds, and the red and blue are the actual received voltages at antenna 1 and antenna 2. Black is the correlated signal if you multiply those two together, and green is what you get when you multiply an average. So it's what would come out of a correlator that's integrating over time long compared to this sort of 1 nanosecond cycle. And if A and B are arriving, if antenna 1 and 2 are arriving in phase, if d sine theta is an integer number of wavelengths, then your average of cosine squared is a half. That's simple enough. If they're arriving exactly out of phase, it'll be negative a half. It's the bottom one. And you notice that if they arrive sort of out of phase, in quadrature phase, a quarter cycle apart, they'll average to 0. This actually explains why in interferometry we don't want our signal to oscillate between positive and negative and 0 signal all the time, to have our source response go away whenever we change by half a wavelength in or a quarter wavelength in projected separation. And so a real interferometer will have a correlator that senses both the in-phase and out-of-phase signals, a complex correlator, and we can represent this visibility as a real part and as an imaginary part that comes from the yellow chain there, where we've delayed one antenna by a quarter cycle. All right, so this is a starting point. What does it tell us about what interferometry is going to do? Well, it does tell us something about the resolution of our interferometer. If you say, I want this F to change by, the argument of this F, this cosine, to change by 1 cycle, then I need 2 pi d over lambda times sine theta to be about 2 pi. And if you work out those differentials, you see that the angular resolution, the small change in angle needed to produce that 2 pi change, is lambda over d. So the resolution of this 2-element weird multiplying interferometer idea is lambda over d. And this is a well-known property. It's more or less what you get from a single aperture, slightly better. We talk about it all the time when we're discussing the resolution of EHT or anything else. All right. Note that we had to assume for the simple analysis that the signal's monochromatic, but no astronomical signal really is. And so it's interesting to ask it, even in this very simple case, what happens if the signal isn't monochromatic? Basically, you have to integrate f over a range of frequencies, and what you find with a little math, which I just skip forward, but you can derive it or follow the slides yourself, is that you get the same f, but it's now multiplied by some envelope function, a sinc function. And the argument of that sinc is the geometric delay times the bandwidth. And so if your geometric delay is large, or if your bandwidth, fractional bandwidth is large, you're going to have problems. You're going to have a very narrow envelope. And so, here are examples of this. If you have at the top, this is the visibility f as a function of hour angle on the sky, where the source is as it tracks relative to due south. And you can see this fringe pattern. It's not a perfect sine wave because this cosine has that sine theta in it. But as soon as you start making the bandwidth slightly larger, so that second plot, you see that this fringe pattern starts to attenuate. So the red and blue are the fringe pattern at the frequency -1% and +1%. And when you integrate over the whole bandwidth, you get the black, and you see it's starting to taper. When you get to just 10% bandwidth at a really short baseline, just 30 wavelengths, this is a 1 foot aperture if we're talking about the 1 millimeter wavelength that's characteristic of EHT. So just a 30 wavelength baseline at 10% bandwidth produces this very strong sinc function where your visibility would go away an hour and a half away from transit. Of course, things like the EHT have baselines of 10 gigalambda, not 30 lambda. And even things like ALMA have baselines of mega lambda in some cases. And so obviously this effect is extremely important, and it leads interferometers to do something called fringe tracking, which is or delay tracking, to remove this geometric delay by compensating it with an electrical delay for the signal from antenna 2. If you don't do this, you can't use any significant bandwidth. In the context of EHT, this is more or less what's done in the correlation stage, where we know how much extra propagation time there should be to each antenna because of its position on the Earth. And we search for the signal we're looking for at the right geometric delay. And if we're slightly off, if we don't know the position of that station to about a foot or so, it's very hard to find it because of this fringe envelope. All right, so we've talked a little bit about the basic properties of how two antennas receiving voltages that are multiplied should respond. Let's consider the case more fully. This is a derivation that I'm not going to go through remotely fully, but I've put it into the slide so that you could track it through yourself. And it is in TMS 15. The basic idea is that if you want to understand what an interferometer is actually measuring when you receive the voltage at two antennas separated on the ground and multiply their voltages together, you can do that by constructing something called the mutual coherence function. What's the average power? What's the average correlation between the voltages received at the two antennas? There are lots of simplifying assumptions that go into this. Most of them aren't terribly limiting. It depends on your situation, but especially for the VLBI case that most concerns EHT, these aren't all that important. I will go through step one and basically skip to step N. The field you'll receive at the two antennas is, just like we saw before, it's an electric field. It has some pattern as a function of position on the ground, and it has to consider the extra propagation time. It's important to keep track of how long it takes the light to get there. And we're going to construct this spatial correlation function between antenna 1 and antenna 2 by averaging their complex electric fields. If we do this, there's going to be this this pre-factor that's the time average source intensity, and then a complex factor that depends on the antenna separation. Now, I'm graying this out because there are a lot of steps here that rewrite these equations and follow some simplifications. But if you go through all these things and you rewrite your antenna separations in terms of X and Y coordinates on the ground that we'll get to in a second, expressed in wavelengths, and you convert the linear positions on the sky to angular positions and so on and so forth, you rearrange everything, you can come out with a simpler looking equation, that bottom thing there. And when you integrate that over the sky, you can define something called the visibility. This is what an interferometer will measure by observing a sky distribution given by ILM, where L and M are angular coordinates, the intensity distribution on the sky. And it's ILM times some complex factor, and then it's integrated over the sky. And the shape of this equation, the integral with this complex phase factor that transforms L and M coordinates to U and V coordinates, is precisely a Fourier transform. This is why in interferometry, if you're new to this, you may hear people say some jargony thing about how we're not measuring an image, we're measuring the Fourier transform of the sky. It's because that's exactly what's happening. We don't get to take pictures with these things. We unfortunately have to take, for each pair of telescopes, a measurement of a single spatial frequency, a plane wave in a specific direction on the sky, from each pair of antennas. And from all of the spatial frequencies we can measure, we try to reconstruct the image that, that produced them, the ILM, the intensity distribution on the sky. So this is an interferometric visibility. It is the Fourier transform of what you have on the sky. There are more complicating factors. You have to include the response of the antenna to the sky. It doesn't see the entire sky in most cases. There are many other things, but the basic concept is we're measuring the Fourier transform. All right, so as I said though, we only get one measurement of a spatial frequency of the sky intensity distribution per pair of antennas. And so if you take as an example an ALMA configuration, so it's a 43 element configuration, configuration 6 is sort of middle to large. You see the red dots on the ground, those are the separations in the antennas over something like a couple, 2.5, 3 kilometers on the ground. And if you ask yourself, how many spatial frequencies am I measuring? You're measuring a lot of them. It's, n times n minus 1 over 2, actually. And in the bottom left, you see how those are distributed. You have, that's not the same array configuration, obviously, because those distances aren't in meters. I don't know how I did that. But anyway, but the point is, it's still a 43 element configuration, and you're measuring lots of different spatial frequencies. And if you let the Earth rotate, and so the source moves across the sky a little bit, you can imagine that the separation of the telescopes will appear to change as viewed from the source. And so you'll measure tracks in the UV plane. And so that gives you a bit more spatial frequency information than you have from that instantaneous sampling. Now, the instantaneous response of something like ALMA, does a reasonably good job of covering the UV plane. Something like EHT that has only a handful of elements. In fact, in the case of the 2017 M87 data, we had at most 4 spots on the Earth observing the source at all times, with a very brief exception when we had 5. So we had very few instantaneous measurements, but we could add up to much better UV coverage by using an entire day's worth of data. The basic properties of this are that the largest UV distances are going to determine your resolution. As we discussed before, the baseline separation tells you the spatial frequency you're measuring, and so the highest you can get is the resolution you'll achieve. And the fact that you can't put 2 telescopes at the same position or overlap them within the size of their apertures means that you're always going to miss some spatial frequencies. And if you're not observing a black hole, but you're observing, say, well, actually, this comes into to be a problem for us for EHT as well, but it certainly is a problem if you're ALMA looking at an extended star-forming region. You miss the large-scale emission, your high-pass filtering in the sky. And so often you have to do something to correct for that fact if you want to really understand what the true image looks like. All right, so these UV tracks are interesting, so let's talk about where they come from. If you think about it, you have telescopes sitting on the Earth, and the Earth is spinning. The source is out in some direction, and the Earth is rotating relative to it. Telescopes are fixed on the ground, so their separation as viewed from the source changes as the Earth rotates. And so the natural coordinate system to understand where the telescopes are relative to each other connects to the Earth. For EHT, or for VLBI in general, we want to define a global coordinate system where you have, where you don't make reference to local south and local east, because of course you need to keep track of a south for each telescope then, and it doesn't make sense. But if you have a local connected element interferometer, typically you define a local coordinate system where everyone knows what south is from ALMA or from you know, any other interferometer, and everyone knows where east is, and so you just define X, Y, and Z, these separations between or these positions of telescopes with respect to those local coordinates. It's useful though to keep track of where the North Pole is because that's the direction around which we're rotating. Now, if you have the coordinate system, you see X, Y, and Z are still in this image, but now we're considering the projection of telescope separations when looking from source direction. So that the direction W there is the baseline toward the source, and U and V are those spatial frequency coordinates we saw earlier. And it's a simple matrix transformation where you connect the separation between the X coordinate, X, Y, Z coordinates of two telescopes. That's what X lambda, Y lambda, and Z lambda are, that the differences in the X, Ys, and Zs of two telescopes measured in wavelengths. You see that, you know, it's fairly simple to calculate what the UV-W separations will be, W being the geometric delay. In fact, if you look at that equation, it's a matrix. If you consider just the U and V lines, you see it's just an expression that involves you know, sine and cosine, and so you can rearrange it into an equation that looks like this. This is an equation for an ellipse in U and V. The overall size, the semi-major axis of the ellipse is x squared plus y squared. The center of the ellipse is the z baseline times cosine of the declination of the source. And the squishedness of the ellipse, the axis ratio, depends on the declination of the source you're observing. So if you're observing something at the horizon, these ellipses turn into lines. But this is why the UV tracks look the way they do. They sort of look elliptical in these planes. Here they sort of look circular because the source is almost overhead for ALMA. But the point is they're following these very simple tracks that are easily calculable. It turns out that that plus U plus V is the same as minus U minus V. So you get two tracks for every baseline, but they're giving you the exact same information. And so that's why it's often represented as having this symmetric pair. All right, so let's talk about how a bunch of Fourier components turn into an image on the sky. You can imagine that if you were sampling different spatial frequencies on the sky, you need a lot of them to construct an image. But if you can simply add them together, this goes pretty well. So we're going to build up an image starting with one baseline and increasing the number. Here's a pair of telescopes. They're separated by you know, about 20 meters. And they have this single plane wave on the sky. And so whatever our source structure is, we don't know, but any, you know, point source on the sky will give us this this plane wave response. As soon as we add a third telescope, which means we have a second and third baseline, we start to measure new spatial frequencies, and that plane wave starts to take more shape. Here they're almost all in the lines. They're measuring similar spatial frequencies, but the point is you're starting to fill in, and as we add more, here's a fourth antenna, so we now have 6 spatial frequencies. You can actually start to see a central concentration in where we're sensitive on the sky. And here's 8 antennas. So we've rapidly grown to 28 baselines. N times n minus 1 over 2 is, 8 times 7 is 56 over 2 is 28. And you see there's a central concentration. 16 antennas, now your response is quite nice. This is a pretty good PSF. It's got a central concentration. The side lobes are very small. If you make the array configuration larger, that central concentration becomes even smaller, though the side lobes become larger because there's more unsampled information. And so you can see that, just by combining the measurements that we have from all these spatial frequencies, just summing the plane waves on the sky, we produce a very, nicely shaped response. We call this in interferometry the dirty beam. It's not a, if your interferometer has a lot of elements, the dirty beam is almost unnoticeable. Much of my early career, where I learned interferometry was the submillimeter array. It's an EHT station, and a lot of the time it had 5 or 6 antennas. It has at most 8, and the PSF was often very ugly. In submillimeter wavelengths we now have ALMA, where 43 elements is sort of the baseline number, and so the PSF will often look quite good. I mean, this is only 16. It gets substantially better when you have 2.5 times as many stations in the array. All right, so let's talk a little bit about, build some intuition about the interferometric response to the sky. The Fourier transform is not something that is natural to think about. So you actually have to think a little bit before you assume you understand what the interferometer will see. And this actually trips up a lot of people when proposing for interferometer time or thinking about what the interferometer actually measures, that it's blurring with the PSF, or that 2 sources will add in a simple way when they don't. So it's worth remembering that the interferometer is going to measure a complex visibility. The interferometer is constructed to produce a complex number because it has those in-phase correlation. Remember the 2 antenna case where we just took the 2 voltages and multiplied them, and we had the quadrature phase correlation where we took the 2 voltages, delayed one by a quarter cycle, and multiplied them again, so that our signal didn't disappear as the geometric delay changed. And so this correlation gives us a complex number, and we shouldn't forget that we can express it as a real part and an imaginary part as the 2 correlator outputs, or we can express a complex number as an amplitude and a phase. And in the following, I'm going to plot some interferometer responses as amplitude and phase so that we can see what happens. All right, so here's a simple case. We have a point source. It's on the sky. It's represented by that white square. It's offset from the direction you're pointing. And the Fourier transform, the visibility amplitude of that is a constant 100 Janskys. At all points in the UV plane, the visibility amplitude will be 100 Janskys. But that doesn't mean that we only need one baseline to make this measurement to discover what the source is. Because if you pick any position in the UV plane, you'll see that its complex phase is changing rapidly. The rate of change increases as the source moves away from the center. So the further it is from the center, the faster this complex phase is wrapping. This sort of tells you that the complex phase indicates where a source is on the sky. If instead of a point source, you have a Gaussian source that's also offset from the phase center, it's the same position. What you see is that instead of having uniform response everywhere, you have the visibility amplitude is the Fourier transform of a Gaussian. And the Fourier transform of a Gaussian is another Gaussian. So where this was narrow in this direction, well, I don't know actually whether the camera reverses my motion or not, but anyway, to me this looks right. It's narrow in this direction, it's wide in this direction. That's reversed in the Fourier transform. The Fourier transform of a narrow Gaussian is a wide one in this direction and a narrow one in this direction. And it's centered in the UV plane. So even though your source was down there, the visibility amplitude doesn't encode the source location. The Fourier transform amplitude is centered at 0. The Fourier transform at 0 is the integral over the sky, so it has to peak at the center. But the phase again shows you that rapid wrapping. And outside that sort of elliptical area, it's just numerical noise, but in the elliptical area, you have this coherent phase wrapping that's again telling you where the source is on the sky. And so again, the visibility amplitude structure is telling us something about the shape of the emission, and the phase is telling us where that emission is on the sky. This is a key insight. An unfortunate thing, and something that I leave for the next lecture, is that inherent to the VLBI measurement, so the stuff we're concerned with for EHT particularly, is the loss of most of the phase information. Because there's an unknown amount and different amount of propagation delay above each site due to the atmosphere, we lose track of the absolute phase. And so, you know, we have to keep this in mind when we're trying to make images from the EHT, but that's 2 lectures from now, I believe. All right, so let's consider this a bit further. Let's see how important the phase is. Imagine you have a picture of, you know, EHT's founding director, Shep, and you have a picture of a Roomba. If you take the Fourier transform of these 2 things, and you take the visibility amplitude from the Roomba and the visibility phase from the picture of Shep, so that would be the image in the lower right, you know, it's not clear what will happen. Maybe you just get gibberish. It turns out that because the phase is encoding where the emission's coming from, even if you're really wrong about the visibility amplitude, even if you're getting it from the visibility amplitude of a Roomba, you can get a pretty good picture of Shep. He kind of looks like he's playing Dr. Manhattan or something like that, but it still looks like Shep. And in fact, the same thing is true if you take the visibility amplitude from Shep and the phase from the Roomba, you reconstruct a vacuum cleaner. So the phase is really crucial, and that's part of why it's so difficult to make images from EHT observations, and why you know, so much effort has gone into being as smart as possible about how we make those images. Again, that's a topic for future lectures. Just to treat one more thing about the visibility of complex sources. Imagine that you have 2 sources that are, neither of them is simple point sources, but it doesn't matter, it would still work with point sources, but they're separated on the sky. So we've already seen roughly what the Fourier transform of an elliptical source will look like. The circular source will respond similarly, but because they're separated on the sky, when you add their visibility amplitudes, you have to remember that you're adding complex numbers. And so you don't get the simple addition of the visibility amplitude patterns. You get this sort of beating. You can see the amplitude is oscillating very quickly, and the further apart these 2 sources are, the more quickly that amplitude will oscillate. And so this is just showing how difficult it is to interpret source structure on the sky if you don't know exactly what it is, because almost anything can happen when you're adding you know, the Fourier transform, the complex numbers of these that come from these source structures. All right. Finally, let's talk about what an interferometric measurement, when you reconstruct an image from imperfect UV coverage, does to your source structure. At the left is some sample UV coverage that I constructed from one of the interferometers I worked on for a few years as a postdoc. And at right is the Fourier transform of that UV coverage. It's the dirty beam from that source. So imagine that this is your interferometer, and that, you know, nature has presented you with some sort of toroidal emission structure that you'd like to image, some sort of, I don't know, donut on the sky. And so imagine that there's your donut, and you observe it with that interferometer, that dirty beam, now zoomed out a bit. This is what you will see. You see that the image is messed up by the measurement. It's convolved with that dirty beam. And so understanding what you've actually imaged depends on deconvolution techniques or image reconstruction techniques that try to get you closer to the underlying emission. Again, in the case of VHT, we've approached this from several angles, and that's a topic of a future lecture. But, you know, it's essential when thinking about what interferometers actually measured to remember that the images they produce are convolved with the response of the interferometer, and that response of the interferometer depends on exactly which spatial frequencies you're actually managing to measure. And so with that, I will leave it there. I want to remind you, this link is in the chat window as well, but you can type it out simply enough. Take the survey. Remember that there are webinars coming up, several of them, about dealing with the interferometric data, about how we do image techniques, and how we analyze the interferometric measurement directly in the visibility domain without worrying about imaging. I think I'll hand over to Dimitrios to field questions.
Thank you very much, Dan, for this really nice introduction to interferometry. It's time for everybody to chime in with their questions or comments. Please, if you do, write something on the chat and I will give you an opportunity to talk. Just give another minute if somebody wishes. Oh, somebody raised their hand. I need to figure out. Ivan Rodriguez. Go, Ivan.
Haven't heard you yet, Ivan.
You might want to unmute yourself, Ivan.
Hello, can you hear me?
Yep.
So I just wanted to ask you about the effect of the atmosphere. I know that the turbulence of the atmosphere can change the phase of the electromagnetic wave. So is this taken into account when measuring the phases?
So this is a very good question. So in a normal, I didn't go into this because I thought that for the EHT application it might be a little confusing because we do something different. But in a normal connected element interferometer, what you will do is alternate between a source of known structure, typically as point-like a source as you can, that's relatively close on the sky to your science target, and your science target. So you'll look at the source on the sky that you know will have this simple Fourier transform. You'll measure the arrival time of the wavefront, the phase at each antenna, due to the extra atmospheric propagation distance on top of the geometric propagation distance, the variations in the atmosphere from primarily, at least at sublunar wavelengths, the water in the air, which is not uniformly distributed through the atmosphere. So you'll measure that extra atmospheric delay and you'll correct for it on your science target where you don't know the underlying visibility structure. And so you don't know a priori what the phase should be. And at that point, you can take the measured interferometric visibilities with their corrected phases and try and construct an image. Does that answer your question?
Yes, thank you.
Thank you, Ivan, for the question. Any more questions from anybody? Feel free to raise your hand virtually on Zoom or put something on the comments. And I guess we're going to continue this conversation with a lot more detailed issues next time. From Joshua, how does phase error cause problems for image reconstruction?
So, you know, although I said you can reconstruct Shep from a Roomba, let's see, there we go. You note that when you have the phase badly wrong, this Roomba doesn't look perfect, right? And so, sorry, when you have the visibility amplitude very wrong, the Roomba doesn't look perfect, but you can say that, you know, the picture of Shep in the lower right is the Roomba visibility amplitude with very corrupted phases. So this is the problem, is that, you know, phase errors will rearrange flux in the image because the phase encodes where the emission is coming from. And so, you know, calibrating this out and techniques like self-calibration, where you try and guess the emission structure and then measure deviations from it in your image and identify small corrections to the antenna phases and produce a new image that's slightly better, and again measure the phases and again apply those to the antennas, allow you to try and step the image closer to what you hope it is on the sky without being able to perfectly correct the atmospheric phase.
Very good. We have a question from Ioannis Misirlis. Ioannis, you can speak if you unmute yourself.
Okay, can you hear me?
Speak a little louder, yeah.
Okay, so my question is about polarization measurement. How are the visibilities affected when we try to measure the polarization and not the total flux of the source? Are they just yeah, okay.
So that it's a great and rich question. So the answer depends on a lot of things. So let's talk about linear polarization to be concrete. And then if you think about it, you know, if you want to measure linear polarization with an interferometer, it turns out to be very useful to do that using circularly polarized feeds, so that if you have a circular polarized feed observing linearly polarized emission, as the polarization vector rotates on the sky, say as the source goes over the sky and it's rotating, that just corresponds to an arrival phase in the circular polarized reception. So part of this is something that you can calculate from first principles, again, because just like we know the geometric separation of our telescopes, we know how the sky is viewed from our particular telescope and the way its receiver is mounted, how the sky rotates relative to the receiver as we track a source across it, across the sky. So we can compensate for that part, but we don't usually know the intrinsic polarization of the source. And so you have to measure the correlation between the left circular feed on one antenna and the right circular feed on another. And you have to measure the reverse of that. You have to compensate for these field rotations, as I talked about, but also for corrupting polarization that the antennas introduce. You know, again, it's a rich subject. I direct you to a chapter in my thesis if that weren't too you know, self-serving, but there's lots of literature on it, and actually probably best to talk about offline, except to note that we, you know, the parallactic angle modulation is definitely part of it. We can correct for that, but you know, you have to think hard about how you make a polarized image from the Fourier transform of what you measure after correcting for that.
I think we have time for one last question. Wei, I think if you unmute yourself, you should be able to talk.
Hello, can you hear me?
Yes.
Yep.
Yeah, hi Dan. And usually how long one takes to calibrate like for the actual observations? So it's either from the atmospheric fluctuations or possible phase errors.
So this is a highly wavelength dependent answer. You know, if you will be corrupted by different things at different wavelengths. At long radio wavelengths, it's the ionosphere. At sort of centimeter wavelengths, it's primarily the dry atmosphere, and at submillimeter wavelengths, it's certainly the water in the atmosphere. It depends on site. So just depending on how quickly the air is moving across the array and how widely separated the array is, how high in frequency you are, because if you imagine the same amount of water vapor passing over your array, it will produce a constant delay in millimeters. But if you're observing at 1 millimeter or 0.3 millimeters, the phase change that introduces is very different. And so you have to calibrate more quickly if it's going to produce a larger phase change. So, to be concrete, if we're talking about, 1 millimeter-ish wavelength, things like EHT and workhorse bands for ALMA and SMA and other millimeter interferometers, it's a few minutes to 15 minutes when you'd like to do this calibration.
I see. Okay, cool. Thank you.
Yep.
Okay, we're hitting the hour mark. So I just wanted to thank Dan very much for the wonderful presentation. Thank you everybody for participating. This was, we had over 50 participants at some point, which was superb. Please fill the survey, that the link is on the chat window, because that will help us with the future webinars. And I hope to see all of you in the next webinar on the 11th about VLBI data analysis. Thank you all.
Thank you.